move without being in contact. What is a field? Well, let's assume we aren't talking about somewhere that a farmer puts his cows or plants his tulips. What do we actually mean when we talk about a field in physics? Well, first of all, let's talk about something we all have a feel for. Contact. See what I did there? If you walk up to a chair and give it a hard push, it'll probably move. Well done, you! You have transferred energy to the chair by having physical contact with it, by touching it. Let's leave aside the very strange physics around the fact that nothing ever really touches for now. When I was a kid, I used to watch a show called Xena, Warrior Princess. It was so great. It was about this warrior woman, Xena, who lived in an ancient Greek fantasy world full of myths and magic and monsters. She had this amazingly distinct war cry. Just for the record, that picture isn't Xena. It's a woman dressed as Xena, because I wasn't super keen on invoking the ire of the copyright people. Anyway, before I get lost in reminiscence, Xena ended up developing powers where she could move things with her mind. Kind of like the 90s OG version of Harry Potter's Accio summoning spell. Generally, things that were further away were harder for Xena, and Harry Potter if I remember correctly, to have an influence on. So let's be clear. Xena somehow gave energy to something, moving it, accelerating it, without touching it. So this idea of having an influence on or interacting with something without actually touching it is how we think about fields. Xena, or Harry if you like, is the object producing the field. I'm going to call it a minefield. I know, panorama. And Xena's chakram, an awesome physics-defying circular weapon, or Harry's broom if you want to keep it 21st century, is the object being acted on at a distance by the field. Two important things to note here. Xena and Harry are acting on one specific object, whereas objects that produce fields will interact with any other object that has properties allowing that object to interact with the field. So you can imagine all the weapons in the vicinity being summoned by Xena at once, or all the brooms being called by Harry. Well, on that particular imagery, I don't think I'll be sleeping tonight. The other thing to note, and this might blow your mind a little, is that a field, it's not a real physical thing. It's actually just a model. The way we describe an object's effect on other objects around it without touching them. There's no action to happen until that second object is actually placed near the first that's producing the field. Typically, how much an object can interact with another object within its field will depend on the distance between those two objects. Just like Xena or Harry, if there's no chakram or no broom, there's no field and no interaction. Hopefully, you already know all about vectors, which have a magnitude, or a size, and a direction, such as left or up or north. When we talk about fields, we use vectors to show the size and the direction of the field at that particular point in space. Close to an object, for example an electron, the arrow tail is large because the field is strong, whereas further away, the arrow tail is smaller because the field is weaker. We also use vectors to represent forces. It is very important that you know whether you are using vectors to represent a field of an object or using vectors to represent forces between objects due to a field. But we'll cover that in upcoming mini-topic videos. Field arrows will usually point inwards towards the source or outwards away from the source. In Unit 3, Area of Study 1, the focus is on gravitational, magnetic and electric fields. The take-home message here is that fields are the same thing really, the same idea. One thing can act on another thing at a distance due to the internal properties of those two things. Gravitational fields are the interactions of mass. It's always attractive, as far as we know. A gravitational field refers to how one clump of mass attracts another clump of mass at a distance. The force of that attraction depends on how far away the two clumps of mass are and how much mass there is in the clumps. Electric fields come from charges. For example, positive protons and negative electrons. An electron acts on electrically charged particles in the space around it. How much force depends on how far away that charged object is from the electron. Opposite charges attract, whilst like repel. It is a general rule of thumb that we draw the direction of an electric field as that a positive particle would accelerate if dropped into the field at that location. That's why in diagrams, electric field lines point in towards electrons, because that's the direction a proton or a positively charged particle would accelerate. Magnetism is kind of cool. Objects have magnetism due to the movement of charges. For example, electrons spin. Check that out if you're keen for a bit of extension. And again, the effect on a nearby magnetic object will depend on the distance to that object. Field lines always join a north to a south pole, and convention has us drawing them coming out of north poles and going into south poles. Or, if you had a north pole and you dropped it anywhere in the field, which direction would it accelerate? It's quite similar to the electric field convention. Now for a quick summary. We use fields to model how one object can interact with another object at a distance without actually having physical contact between the two objects. Fields are not real physical things, they're just a way to help us describe how one object can act on another at a distance. We use vectors to show the strength of a field, stronger close to the object and weaker further away. Internal properties of objects enable their interactions through fields. Gravitational fields are the interactions of mass. Electric fields arise from the interactions between charged particles, and magnetic fields result from the interactions of moving charges. This has been Red Lipped Astro with What is a Field? Please feel free to like and subscribe, or leave a comment below if you wish.